So welcome back. And the topic this week is a continued discussion of Wick's theorem, which we discussed last week, with examples. So this is something which takes some time to build up an intuition about. And then one of the other things which I wanted to do is actually to discuss parts of the exercises this week. And there is a reason for that, and or actually many reasons. So this kind of model, which you will see introduced in the exercises this week, is called the Lipkin model. It was introduced actually in nuclear physics back in the 60s. And it's been an extremely popular model because you can rewrite a Hamiltonian in terms of creation and annihilation operators, and you can rewrite it in terms of Pauli spin matrices. This model has been a model which has been widely used in quantum computing, because in quantum computing, you would actually translate many of the operations in terms of operations on Pauli spin matrices, in terms of spin matrices. So it's a model which has been in a way resuscitated. It has gotten a new life in the sense that it comes together with models like something called the Hubbard model, the Ising model, so-called spin models, which are widely used in quantum computing. But also it has a lot of nice physics. So we can actually interpret many physical systems in terms of these different types of excitations. So it's a model which lends itself to many interesting interpretations and applications. And it represents in a way a kind of simplified approach to a physical system. At the same time, for some simpler cases, you can even solve it analytically and hopefully then gain a lot of insight about the physics of the system. Another thing which we need to discuss a little bit, which we haven't done yet, is to determine the dates for the midterms. So the midterms are typically handed out, the first one in the beginning of October. And then we roughly work on this for 1 week, 10 days, 7 days or 10 days. So it's just a classical take-home midterm exam. So I was thinking of handing out the first one around the 5th or 6th of October. And then we will have the next one in the beginning of November. And we also need to decide when we want to have the final oral examination. So I would just like to have some feedback from you when you guys are away or unavailable, so that we can set the deadlines and so on, so that it makes it the easiest possible way for you guys. Then so for the final oral examination, one of the things which we normally have landed on is the third week of December. So in this year, I think it's the week which begins with Monday the 16th, I think. And sometimes during that week, because then most of you are done with the final examinations in other courses. And in case you are going back home, we have always run this exam via Zoom for those who cannot be here, cannot be present physically. So normally we try to schedule it during that week. So that's typically the week around 16th, 17th, 18th of December. So please just send me an email with your constraints and what fits best, and then we will try to adapt to that. Then on Friday, we are going to begin with what's called the particle hole formalism. So let me go back to the whiteboard. Oops, I think what happened? I think no, here we are. So let's just do that one. So let's just quickly remind ourselves about Wick's theorem and some of the notation which we did last week. So Wick's theorem and notations. Wick's theorem notations and examples, with examples. And one of the things which we also did last time was to introduce this diagrammatic notation, which we will use quite often because that simplifies often the way we represent physical processes. So Wick's theorem, just to remind you quickly of that one, says that the expectation value of a string of operators is given by the normal order product of this string of operators plus the sum over all possible contractions of pairs of operators, just one pair, and this is normal ordered, YC up to W, and we indicate that operation of only one set of operators, which is now contracted. I'm going to bring back the definitions of that, of the contraction. And then we have two possible contractions. And as we discussed last time, it's only the case where we have an equal number of creation and annihilation operators, which gives us a result which is different from zero. And now we have two possible contractions. And this goes up all the way up to M, which is a number of operators divided by 2. And then we are looking at the normal order product of all the contractions which we can make. And then we would write this like that. And this would be contracted again. So that's Wick's theorem. And the contractions were defined in the following way. So if we now go back to the way we wrote the contractions. So we have defined, if we now look at two operators, one creation and one annihilation operator acting on the true vacuum, so this is an expectation value. This is something which we know is equal to delta alpha beta minus A beta, and we know that this last term is identically equal to 0 because we have just the action of an annihilation operator on the true vacuum. So remember now that the true vacuum is a vector with no filled single particle states. And we rewrote this one in terms of this notation which we introduced last week, a contraction, plus the normal ordered set of operators A alpha, A beta. And what we had is that this A alpha, A beta dagger, this contraction here, is just equal to the Kronecker delta. And then since these are now particle states, I mean, there are no states below the vacuum, then we have to obey the following rules. So this is equal to 0. But we are going to modify this contraction when we introduce the particle hole formalism. And then this is also equal to the contraction of two operators of the same type. So all these contractions, all these three contractions are equal to 0. And you see that immediately because if we have two creation operators acting on the vacuum state, and then we take the vacuum to vacuum expectation value, this has to be equal to 0. So this was a quick reminder of Wick's theorem. Now, one of the things which we also discussed last week was the rewriting of one body and two body operators in terms of second quantized operators. So we had for the energy Hamiltonian, we had a one body operator H0, which we can now rewrite in terms of a sum over all the available single particle states. And then we have these integrals, which we often call for just matrix elements, because we will rewrite them in terms of matrices. So you can then think of looking up a matrix with specific indices, and then you will just fetch that specific matrix element. and then we had an A alpha, A beta. And then we had the interacting piece, which is a two-body operator. And that is has a sum over 1/2, alpha, beta, gamma, delta. And we have an integral again, which we defined in the beginning of the semester. And this has a gamma delta. And then I have a creation operator and a new one. And then I have delta of A gamma. And these two are interchanged, and this follows from the Pauli principle. You will often also see this one written out in terms of the anti-symmetrized matrix element. And in that case, you would see this being rephrased in terms of these matrix elements, which are anti-symmetrized, where we have the so-called direct term minus the exchange term. And this is multiplied with A alpha, A beta dagger, A delta, A gamma. So in many cases, people skip the subscript AS and simply just assume that when you have this factor 1 divided by 4, that this is you implementing an anti-symmetrized matrix. So these were just derivations which you can also look up in the lecture notes from last week. Now, the other thing, yeah. Yes, so you just compute. So instead of you having a table where you have only just the integral, you have a table which now includes two integrals. And that saves time. So for you, for instance, doing shell model calculations in nuclear physics, often the matrix elements are anti-symmetrized. And just to remind you quickly of that, so this alpha, beta, so these are integrals, and we sloppily call them for matrix elements because we tend to rewrite everything in terms of matrices. So this is an integral, which we call a direct term, minus alpha, beta of the exchange term. Now, this can be very convenient from a computational point of view in case it takes time to evaluate the integrals. Suppose you're evaluating the integrals on the fly, then you may have to evaluate both of these. But if you can pre-calculate these integrals, then you will simply sandwich them into one term only. And when you then look up in a table and you have the indices alpha, beta, gamma, delta, then you're fetching both elements. And that saves computational efforts. Now, the other thing which we did last week was to look at a diagrammatic representation. But let me just set up, for the sake of completeness, what we labeled as a one-body operator. And that is in general written in much the same term as the previous one. So I have an alpha, and then I have a one-body operator. So this could be an operator for electromagnetic transitions, where you act at one particle at a time. And this would then be given simply by this expression here, or beta. And then we have the general two-body operator, which then can be written either with anti-symmetrized matrix elements or with just the one matrix element. And then we would have an alpha, beta, and we have the one-body operator and two-body operators of gamma, delta, anti-symmetrized, multiplied with A alpha, A beta. So the expression is essentially the same as the one we had for the energy or the interaction between two particles. And this is something which is then strictly reserved to fermions, because when we have bosons, we don't need to have these anti-symmetrized matrix elements. So if you're looking at the bosonic system, you would then often just leave out this anti-symmetrized matrix, and we would actually not include them. Then let's look at the diagrammatic representation. Let's quickly repeat that. And then we're looking at examples afterwards. So the way we represented this contraction is typically by setting up a line like this. So we have a state beta, which gets annihilated, and then we have a state alpha, which then gets, no, the state beta, which gets created, and then we annihilate it. And we would typically write it like this. So where we indicate that now we are performing a contraction. So in principle, what you often would see is something like this. You have two states, alpha and beta, and these are being contracted. And we normally just, for simplicity, we would take away this contraction symbol, and we would just draw a line with an arrow. So at the end, you will see a typical notation where this one just is given by an A alpha, A beta dagger, and this looks like this. And since we have a Kronecker delta, this means that we have the same state in and out. When we then look at the operator, this H0, this is then rewritten in terms of the following. So we often skip the summation, alpha, beta, but in principle, there is a summation. And this is to indicate this cross here, to indicate that this is a one-body operator. And we have left that unspecified, undetermined. And we would set up arrows. So we would have a, if we look at the expression, the mathematical expression, it's given by an alpha beta, and then we have an alpha H0 of beta multiplied with A alpha, A beta. So we would have the outgoing state here, and then we have the incoming state beta here. And it's pretty normal to skip the summation over alpha beta for simplicity. So it's pretty common to just rewrite it like this. So you have an incoming state and an outgoing state. So this is the beta state here, and this is the outgoing state alpha here. And then the quantity which you see here is now representing this operator H0. And then you can replace this cross with other types of operators. Sometimes people draw it like a box, or you can just choose the way you want to draw it. Then if we look at the two-body operator, which we had, so this H over I, this is something which you will see now. If we don't have an anti-symmetrized matrix element, it will often just be written like this. So you have an incoming states, gamma and delta, and you have the outgoing states, alpha and beta. But if you go back to the expression, what you had is that this is now representing 1/2 sum of alpha, beta, gamma, delta, and then we have an integral alpha, beta, and V of gamma, delta, and then we have the anti-symmetrization, no, the creation and annihilation operators multiplied with A delta, A gamma. And the way you would read this type of diagrammatic representations is that this state, which you see here, this one, that represents this incoming state, gamma delta. And the state which you see up here, so to the left, we have the state alpha, and to the right, we have the single particle state beta. And this term which you see here, this one, represents the interaction itself. So when you see a diagram like that, you can think of this as the result of a specific operation. So sometimes the notation can be a little bit confusing, because sometimes this can be the result of a specific calculation of an expectation value, or you can use the same diagram to represent an operator. So in a way, you have to tell from the context what is what. And typically, when you now compute, as we did last time, when we have an expectation value of, let's say, a two-body state, like an alpha 1, alpha 2 of hi, of alpha 1, alpha 2, we know that this one, when we run the calculations, when we now take the full Hamiltonian here, this was given by the matrix elements of alpha 1, alpha 2, of V, alpha 1. So this goes back to what we did in the beginning of the semester. And we calculated this one using either standard first quantization by setting up the integrals. That was one of the things we did the first week. Or we can actually set it up using second quantization. And this state, which we looked at, alpha 1, alpha 2, is then equal to an A alpha 1 dagger, A alpha 2 dagger, acting on the true vacuum state. Yeah. So that follows from when you use the spectral decomposition to rewrite the operator from first quantization to second quantization due to the Pauli principle. That comes actually from that. So the derivations which you have in the notes from last week and the week before, you can actually go through that one and you will see that due to the Pauli principle, these two have to be interchanged. So that's simply due to the Pauli principle. And you will find that derivation in the notes. I actually just went quickly through it because it's not a very exciting exercise. And when you do these interchanges and swapping of indices, etc., then in order to represent correctly the anti-symmetrized operator, you have to interchange these two states. Okay, so the thing which I also wanted to do now is to quickly remind you a little bit of how we did this calculation. And just as an example, because you will also find that useful when you go to the exercises. So let's quickly repeat the calculation of this expectation value here using second quantization, just to convince you that we do get these expressions. And then we are going to reframe it in terms of a diagrammatic representation so that you can see both ways of doing that. And the diagrammatic representation is often very powerful because you can actually use graph techniques to figure out the same expressions which you would get by lengthy calculations. So that has been a big kind of part of many-body physics to use the symmetries which would bring into the different diagrammatic representations and use those to actually calculate expectation values. But let's quickly remind ourselves of this specific expectation value going through the calculation using Wick's theorem. So just as a reminder, we did that last week, but let's quickly repeat it. So what we would have then would be a summation over the matrix elements, alpha, beta, gamma, delta. We have the specific matrix element here. So we sum over all these indices. And then we have now to calculate, using Wick's theorem, this term here, where we have an A alpha 2, A alpha 1, and then we have the operator A alpha, A beta, A delta, A gamma, and then we have an A alpha 1 dagger, A alpha 2 dagger acting on 0. So this is the expression we need to evaluate. And with Wick's theorem, we know now that the only term which remains is the one where we have contracted all the operators. So keep in mind also another thing is that using Wick's generalized theorem, which is just something which follows from the definitions of the different contractions, we are only taking contractions between sets of normal ordered operators. And that follows simply from the fact that if I want to take this contraction here, that is equal to 0. If I take this one, that is equal to 0. So all contractions within an operator, which is already normal ordered, because you see now the operator itself has all the creation operators to the right, to the left, and the annihilation operators to the right. This is already normal ordered, and the same with this one. So when I take contractions, if I just list all the possible contractions, this one is automatically 0. This one is 0. So the only possible contractions which are non-zero are those between sets of normal ordered operators. It's pretty easy to see that, right? So let's take now a look at this terms here. And it's pretty common when you look at these contractions to just skip the vacuum expectation value. And you would just rewrite it in terms of an A alpha 2, A alpha 1. So we just leave out the vacuum to vacuum expectation value and use a more compact notation when we are performing the contractions. So one contraction which we have, as we discussed last week, is obviously this set of contractions here, where we have the contractions with the nearest operators. And this gives us simply a matrix elements. You see you have an alpha 1, which has to be equal to gamma. So that means that gamma here is alpha 1. The alpha 2 is equal to delta. Alpha is equal to alpha 1. And beta here has to be equal to alpha 2. So when I introduce all the Kronecker deltas from the contractions, I can immediately write off this term here, alpha 1, alpha 2, the interaction, alpha 1, alpha 2. So that's one integral which we need to evaluate, unless we have pre-calculated that integral. So then, when we now look at the contractions, we can now, I'm going to just rewrite this term by term. And then we have an A beta. So let's just keep this one as it was from the previous case. So you see that when you do these contractions, there are only 4 possibilities, which are non-zero. 4 sets of contractions. And then we have an A delta, A gamma, A alpha 1, A alpha 2 here, dagger. And now we interchange these two guys here. In order to achieve or to be able to perform the contraction, we have to move this operator to the one we want to contract it with. So doing that, we just interchange these two creation operators using the anti-commutation rules for these two operators, and that gives rise to a minus sign. So in this particular case, what you see now is that delta is equal to alpha 1 and gamma is equal to alpha 2. And the previous one is just unchanged. So that means that what I get then is a new contribution, which is minus, and then I have alpha 1, alpha 2 as before, and then I get minus this term where I have now interchanged alpha 1 and alpha 2. And then we can do the same exercise again in 2 more times. And then when we have done that, so let's just set up all the terms just for the sake of completeness. So let's now also perform the interchange here. That one, so we will have this contraction, and then we have the same one as we had before, which is that one. In this case, we need to interchange alpha 2 with alpha 1 again, as before. That gives rise to a minus sign, and then we can perform the contraction with gamma and alpha 2. Then I need to do the same thing here. So in this case, it means that alpha 1 is equal to beta, alpha 2 is equal to alpha. So I get 2 minus signs. And normally it's pretty normal when you set up these contractions to indicate that a minus sign arises when you have such contractions which cross each other, because that means that you have to interchange two operators. So this then becomes equal to a plus, minus, minus, but now I have alpha 2, alpha 1 of V, alpha 2, alpha 1. But we know that these integrals, we have defined this interaction to be invariant under the interchange of alpha 1 and alpha 2. So this is the same as alpha 1, alpha 2 of V, alpha 1, alpha 2 here. This is just the term, which is an integral, and we interchange particles 1 and 2. And we have assumed now that the Hamiltonian contains an interaction piece, which is invariant under the interchange of particles 1 and 2. So that means that the integral stays the same, the value of that one. The final term, which we need to include then, which is the contraction, which is also giving a non-zero result, the final one. So the only one which we didn't take into account is this one. So we keep these two guys like that, but then we have this one here. And that gives rise to a minus an alpha 2, no, sorry, alpha 1, alpha 2, alpha 1 of V, alpha 1, alpha 2, which is the same as minus alpha 1, alpha 2 of V, but now we interchange alpha 2 with alpha 1 here. And you see now that when I collect these terms, I get 2 of each, but then there is a factor of a half in front here. And that means that I'm simply left with what we got in the very beginning of the semester, alpha 1, alpha 2 of V, alpha 1, alpha 2 minus alpha 1, alpha 2 of V of alpha 2, alpha 1, which we could rewrite in terms of this anti-symmetrized matrix element. Now, when we now look at this diagrammatically, we can then write this in a more compact way. So if you go into the textbook by Hjorth and Bartlett, they have a notation of which they've been using for the state alpha 1, alpha 2 here. So if we just look at that state. So sometimes they use this notation where you have 0, which is just indicated by this line. And then you have created two states which are filled with one particle each. So this is one way of representing that one. But in many textbooks, they skip this term which you see here. So I'm going to skip that term myself. But in Hjorth and Bartlett, they have indicated in particularly that the vacuum state, or when we now introduce a particle hole notation, you will have a different vacuum state or reference state. Then it's often indicated in terms of this line here, just to indicate that this is the state you're acting on. But I'm going to use more a notation which you will see in many other textbooks, which looks like this. So this is up to you, which one you prefer. So when you then are going to do the contractions, when we look at this diagrammatically, you can now think of, let me just rewrite it like this. So we have the state alpha 1, alpha 2 here, and then we have the interaction, where we have a gamma delta, and then we have the alpha beta, and then we have the final state here, which is also an alpha 1 and alpha 2 here. So what you would do then typically is to indicate the contractions. So the first example we looked at, we contracted alpha 2 with beta, and we contracted alpha 1 with alpha, and gamma with alpha 1, and delta with alpha 2. And when you perform all these contractions, then we are changing the labels. And the specific matrix element, which we were looking after, would then be labeled like this. So I have an alpha 1, alpha 2, alpha 1, and alpha 2. So this diagram is something which you then, so one thing you have to be a little bit careful always, because in here, sometimes people would also write that you're summing over alpha, beta, gamma, delta, all the possibilities. But we are going, sometimes you will see a difference in textbooks. Some people will insist on keeping this summation, or they may have some different notation for the operators. So I'm going often to skip that summation, and implicitly, what I'm going to say is that this is an operator which is acting. This sums over all the possible single particle states, but when we then perform the contractions, we pick a specific set of single particle states. And this translates, when you have this diagram, this translates into an integral, which you then can look up either in a table, or you would have to calculate it. So the diagrammatic representation is very powerful because you can then, from this one, you can just read off an analytical expression. So one of the other contractions which we looked at was the following. So we still had alpha 1, and then alpha 2 here. Then we had the operator. And then we have the incoming state, alpha 1. So you can think of this as your system being prepared in a state, and then there is some interaction between the particles, and then the state can scatter into another state, or it can go back to itself. So in this case, we're calculating an expectation value, and in the first case, we will be calculating a transition probability. So one of the other cases which we looked at was actually us making this contraction here and this contraction. So that corresponded to A delta, A gamma, A alpha 1, A alpha 2 here. And when we perform that contraction, and then we had this possibility where we just contracted these ones. That gives us, when we now are writing the final diagram, there is no minus sign here, but we would just draw the diagram. So we would have an alpha 1 coming in here, an alpha 2, and then we have crossing fermion lines. So we would have an alpha 1 here and an alpha 2. So this is just a way to draw these diagrams. This one, when you read it, when you read the diagram, when you have fermion lines which cross each other, that corresponds to you having had to interchange two operators. That gives rise to a minus sign, and that means that you read this crossing fermion line as a minus, and then you would have an alpha 1, alpha 2 here, or V, alpha 2, alpha 1. So that means that this anti-symmetrized matrix element, which we have, the final expression which we would need to evaluate, or we have pre-calculated the integrals, it means that this term which we wrote as an alpha 1, alpha 2 of V, alpha 1, alpha 2, anti-symmetrized, which is equal to alpha 1, so let me just rewrite it here, minus alpha 1, alpha 2 of V, of alpha 2, alpha 1 here. When we do it diagrammatically, it looks something like this. So the dotted line is now representing the interaction. I have alpha 1, alpha 2, alpha 1, and alpha 2 plus. because we read off the analytical expression from the diagram. So we always have pluses on the diagrams, but then depending on whether we have crossing fermion lines or not, we would then read off a minus sign or not. So this is the way you would write that matrix, these integrals, in terms of diagrams. So crossing fermion lines gives rise to a minus sign due to the contractions, which are performed. Now, there is a more compact notation here, because sometimes you don't want to carry with you two diagrams or more diagrams, but you would have a compact notation in terms of anti-symmetrized matrix elements, or these integrals which we have defined here, which is given by a direct term and an exchange term. So a more compact notation is often, so these are normally called in non-relativistic quantum mechanics, they're called Feynman-Goldstone diagrams. So because when people did non-relativistic quantum mechanics, they were very much inspired by quantum field theory, where Feynman was the promoter of this simplified pictorial way of representing physical processes. So you can actually think of these as actual physical processes, in the sense that you have particle 1 and 2 interacting, and you end up in a new state. So the system is prepared in a specific state, and there is some kind of transition to another state. So this was the actually, I think Feynman introduced this in 4950, the diagrammatic representation. And that has been a very powerful way of representing physical processes. So for sometimes for some specific many-body theories, you can start drawing all possible diagrams. If you're doing many-body perturbation theory, and you have a term in second-order perturbation theory, which means two interactions, you can often just sit down and just draw all the diagrams by taking into account all possible symmetries, and that corresponds to normally to the analytical expressions you get at the end. So it's a very powerful way of expressing terms in many-body theory. So sometimes this is actually, pushed a little bit too far ahead, because many people think that diagrams in many-body perturbation theory represent physical processes. But the physical process is actually the sum of an infinity of interactions between particles. But it's pretty common, actually, like in particle physics, and also many-body physics in general, to think of specific terms which involve several interactions as the system interacting repeatedly. And some of these processes can then be given a physical interpretation, which we are coming back to this actually. And it's a very, you develop a kind of jargon where you try to interpret physical processes from the diagrams. It's a very powerful way of looking at things. And this is often, so this is something, let's stop here now. So this is called a Feynman. In non-relativistic quantum mechanics, this is called a Feynman-Goldstone diagram. Feynman-Goldstone diagrams. It's common often to sandwich these two into one term. So what you would often see is something which is called a Hugenholz notation, after a Dutch physicist. I think he was Dutch. So that means that you represent the anti-symmetrized matrix element with just one diagram. And then it's common to just write it out in terms of this box here. This is where the interaction takes place. And then you have alpha 1, alpha 2, and alpha 1, alpha 2. So what you have to do then is actually to open the box. And that box, when you open it, will give you a direct term and an exchange term. So this gives you a more compact notation. And many people tend to use that for fermionic systems. Any questions, by the way? So you see, just as a small thing before we stop now, you see that if you have more than just two particles here, then you will have to do many more contractions. And this is going to motivate what comes tomorrow, which is called the particle hole formalism. Because then we can simply stay with some few types of particle states which are defined in terms of a new reference vacuum. Okay, so after the break, I'm just going to do one or two more examples. And then I wanted to discuss a little bit the exercises this week, because I'm thinking of using this model as a part of the first midterm. So doing that one can be useful for the midterm. So let me record it. So what we had before the break was a discussion of the Wick's theorem applied to one type of expectation value. So what I want to do now is to bring up another example. And this example is a Hamiltonian, which we are going to look at in the exercises for this week. And for this particular case, you could restrict yourself to 2 particles, or we can go to 4 particles. And in the case of 4 particles, so these are the exercises for week 37. And the model which we are going to look at is a model which has been used in many, many applications, in particular in nuclear physics. And it's a model which mimics some of the basic features of a nuclear physics Hamiltonian. Now, the type of model which we are going to look at has an Hamiltonian, which is given by the one-bodied Hamiltonian, plus an interacting piece where we have 2 pieces actually, H1 and H2. So this is our interaction piece. And we are going to use this example here, this specific model, to just in a brute force way, calculate matrix elements. And you will see that that is something we can do up to 4 particles. On the other hand, this Hamiltonian is a Hamiltonian we can rewrite in terms of what's normally called a quasi-spin operator. And then we can use the properties of spin operators to set up the matrix which we end up diagonalizing to find the eigenvalues. Now, this model here is something which will also motivate the introduction of our first many-body method next week, which is called full configuration interaction theory, or how it's often called in atomic physics or nuclear physics, the nuclear shell model in nuclear physics, and the atomic physics shell model. So that will be our first many-body theory, which we will apply. And this model here can actually be rewritten in terms of a diagonalization problem when we change the basis set. You can actually rewrite it in terms of second quantization as well. But before we move on now, let's just look at these elements of the Hamiltonian. So this is a system where we have one part here, which has a constant epsilon, and we are then summing over specific quantum numbers p and the spins of the particle. So this is going to be a sum of spins, and we will have the spin value here, sigma, and this sigma can take the values of -1 or +1. And then this is multiplied with the creation operators for specific spin value, and then the annihilation operator for specific spin value, and that state p. So let's take a look at what this looks like. So the sigma can take 2 values, -1 and +1. So what are these p's and how do we set up the model here? So we are going to look at a system with 4 particles. Doing 2 particles is even simpler. And if you do the standard operation with Wick's theorem, etc., then you will see that the two-particle case is something which we can simply transfer from the examples we had before the break. But in our case, we're going to look at 4 particles. So P is now going to indicate specific slots where the particles can be in. So we are going to set up 4 slots here. So P indicates now slot 1, 2, 3, and 4. Now this system here, this state here has sigma equal to -1. So often you would just draw this as an arrow which goes down. So this is just, you can think of that as a spin down state. It doesn't need to be that. It could just be thought of as an additional quantum number which lives in another space than the quantum numbers P. So your state here would be the tensor product of, let's say, one particle in state 1 with this spin part. And then we have the upper state, which has a sigma equal to +1. So only 2 values. And then we are going to have new slots up here, which we could label as 5, 6, 7, 8. So this could be slot 5, 6, 7, 8. So these slots are slots now which indicate specific quantum numbers, which we don't need to specify now. You can just think of, if you have 4 particles now, so with n equal to 4, you could now think of this being a Slater determinant. Then we know that when we have these 8 slots and we have 4 particles, we can distribute them with a replacement in these different slots. So it means that a possible state which we can obtain. So let's look at these different possibilities. And then when we look at these different possibilities, we can go back to the Hamiltonian, because then we can make the whole thing with the Lipkin model is that there are going to be parts of the Hamiltonian, so which can promote one particle from the lower state to the upper state. And we are going to call these excitations. And you can also think, because this becomes very handy when we introduce the particle hole formalism, because then you can think, instead of having 4 particles you're exciting up to this state, you can look at the Hamiltonian acting on, let's say, either this one or both of these, and then these can be promoted up here, for instance. This would normally be called, when we have introduced the particle hole notation, for a 2-particle 2-hole excitation. So we can define then a reference state, which now could be this state here. And that, when we introduce the particle hole formalism, that reference state is normally something which defines our new vacuum state. Defining a new vacuum means a redefinition of the creation and annihilation contractions, the contractions between annihilation and creation operators. So let's look at some other possible realizations of that system. So we could now have, if we now just bring back the same boxes, we could have a state where we keep slots 1 and 2 occupied, but then we could promote these 2 guys up here, and then we would have these 2 slots occupied. So this has still sigma equal to +1 and sigma equal -1. And now this would be a state where we now have promoted 2 particles from the lower state to the upper spin state, if we think of the sigmas as spins. So that's a very natural way of setting up and defining the system. So in order to achieve that, we have to have some operations on that original state. So if this state, which we see here, is an ansatz for the ground state, phi 0, then we would need something which brings us up to this state, if we call this phi 1. So there has to be some parts of the Hamiltonian which allow us to move from phi 0 to phi 1. We can also have other possibilities. So we could define a state which I'm going to call for phi 2 here. And in that particular case, we could now think of just promoting one particle from the reference state up to the spin 1 state. And in this particular case, we could think of a state which looks like this. And then we have promoted one particle up here. That's another possibility, etc., etc. So you have, in this case, you have 8 slots and 4 particles. So the total number of configurations which you can make here, so the total number of configurations is given by 8 slots which you have, and then you're distributing 4 particles. So that means that you end up with 8 factorial divided by 4 factorial, 4 factorial here. And that should be, if I've done the calculations correctly, equal to 70 possibilities. So if I'm setting up the full problem, I would have 70 configurations, which means that I would have to diagonalize a 70 by 70 matrix. However, when we set up a Hamiltonian, we are going to require that there are some specific features which are conserved. So we would typically say that the total spin of a state should be conserved. So that means that if you now look at a state like this one, this has a total spin, which is -1, -1, -1, -1, -4. And if you divide by 2 here, which is common to do because these are half spin particles, then it's a spin -2. And if we assume that this quantity is conserved, it means that a state like this one would then not be allowed in the transition from this state to a state phi 2, because you design often your Hamiltonian so that it conserves the total spin projection. But you can break that one if you want to. So you can actually set up a 70 by 70 matrix with all the configurations and set up the Hamiltonian matrix and diagonalize. This is something we will discuss next week. Now here, we are going to look at the realization of some particular configurations with a given total spin. So you see now that in this specific case, you can have a total spin here for this system here, since you have a factor of a half. So the total spin projection, ms, is equal to -2 here. That's the most stretched state. And you have the maximum value, which is +2, which would correspond to all guys being up here. Now you can, when you look at these values, these extreme values, these are the maximum values. It means that the maximum value of the total spin, if you go back to basic angular momentum algebra, so you would have a total spin equal to S, which is equal to 2 here. So when the total spin is equal to 2, then these spin projections take the values -2, -1, 0, +1, and 2. So one of the reasons why we are going to rewrite everything in terms of what's called a quasi-spin set of operators is that we can then focus on different spin values. And there's going to be a possible set, so you can have an S equal to 1 as well, and that will give you spin values -1, 0, and 1. And then you can have a spin equal to 0, which has also its own different realizations. Okay? So if we assume that the Hamiltonian preserves some of these symmetries, then we can actually reduce this problem from a 70 times 70 matrix to blocks of conserved spin. I'm coming back to this next week. So this is a typical trick which we use in reducing the dimensionality of the problem. Now, in this Lipkin model, this H1 term, which we defined, is now given in terms of a factor of a half times a constant. So that means that these integrals, which we previously had in the expressions, are now just given by a constant. And then we are going to have a summation over only spin. So this is a case where we don't sum over all the single particle states which we can have, but only some selected parts of the Hamiltonian. So there's going to be a sigma and a p prime. And we are going to have a creation operator for sigma and p. We are going to have a sigma of p prime. So sigma here has to be the same for the two states. And then this is multiplied with an a of minus sigma of p prime and an a minus sigma of p. So what this guy is actually doing for us, when we go back to what we had in that image over the possible configurations, if you look at what you have here, you have to be in the same state. And here as well, you have to be in the same state, but with the opposite value. But then the states can be, the single particle states can have different p values. So what does that mean? That means that I could actually be here. So these two guys here can then be kicked up to this level here by the action of the Hamiltonian. So I start with the opposite spin. I end up in this state. And so I have to start here. So I cannot take one from here and one from here, but they have to be in the same spin state. And then I promote them up here. So when we have introduced the particle hole representation, we're actually going to call this for a two-particle, two-hole excitation. So the reason for that is that if we define this as a new vacuum state, then we are kicking up these two guys up here, and we leave two open slots here. And we just call this for holes. So we kick them up here. So this will be particle states when it's filled. And then we leave two holes here. So that's typically called a two-particle, two-hole excitation. So that's a jargon which we use. Yeah?
Usually when those diagrams lines there, usually that indicates that this line represents part of the
yeah.
And then usually like slots within those lines.
Yeah. Yeah.
Here you say that this that's the difference of this right?
Yeah. This is just an inverse ladder of what you are used to. So if you think of, you probably met the nuclear pairing Hamiltonian. So in that case, what you would have is just the opposite of that case. So you could have now the slots like this. So P equal to 1. And you could have a state with spin up and spin down, right? And then you have P equal 2. And then you could have a spin up and spin down. And then you have new slots up here. So you have a double degeneracy. So this model is nothing but just the inverse ladder. Yeah. Back here or? Yeah. These are just slots where you place the particles.
Okay, that's not P equal.
No. So, no. P has different. You can think of that as different quantum numbers. So, like, so it depends a little bit on the counting. So this P equal 1, which you see here, for instance, that could indicate some specific quantum numbers. But when you now are specifying the slots in your computer, you would then set up an array, and then you would have box 1, box 2, box 3, etc. So in your internal labeling, you would have 1, 2, 3, 4. So 3 here points to p equal to 2 as a quantum number. We haven't said what kind of quantum number it could be. Yeah. Yeah, so you could do that. So here I just set it up as an internal labeling, but when you do this now, you actually relabel these as one, as just, this is correct, 1, 2, 3, and 4. So this would just be a kind of labeling which you would have internally in your computer. But now we are going to label these states as one, as you said, 1, 2, 3, and 4. That's correct. So when you identify it, the only thing which changes is actually that. That's correct. Yeah, I was thinking a little bit ahead here because I often tend to think in terms of the way I represent states. And the same thing here, because this is just a ladder. The other one was a ladder in sigmas, and this is a ladder in p's. And in this kind of pairing model is actually also a very popular model. It was, I mean, its origin was the way to explain superconductivity by Bardeen, Cooper, and Schrieffer. And then you just promote pairs. And you can allow for a breaking of pair, or you can conserve the number of pairs. And that means that you would promote this pair here up to that state, for instance. And then the Hamiltonian, which you look at now, which you see here, this Hamiltonian now acts on two particles in the same spin state. It promotes them up to a new state with a different spin, but where the p's are kept. So you would, you're correct. I mean, I was rushing a little bit here. So the quantum numbers would be 1, 2, 3, 4. And whereas here, the quantum numbers would be 1, 2, but the slots would be different because you point to another quantum number as well. Okay, that's very good. So then this other term which we have, so we're going to label this as a two-particle, two-hole term. And we are coming back to that in more detail when we have discussed the particle hole formalism. Then there is a final term, which is we are going to call H2 here. And that's given by 1/2 of W. And then there's a sum over sigma, P and P prime, like that. And now we have a term here, which goes like A of sigma of P dagger. And then I have A minus sigma of P prime. And then I have an A minus, A of sigma of P prime and A of minus sigma of P. A of minus, A of sigma. This is not a minus, this is just sigma here. And this is minus sigma. Got a little bit unclear. Yeah. So this one is something which now acts on the following type of state. So let's take a look at that. So we have the p's. So let's just put the p's now 1, 2, 3, 4. So we have 1, 2, 3, 4. 1, 2, 3, 4. And we have sigma equal to 1 and sigma equal to minus 1. So this is going, suppose now that we have the ground state, which is being filled, or rather, it is now actually a operator which acts on a state where you have, let's say this has a sigma minus 1, and then here I can have a sigma plus 1. So this is a state which I have set up, and then I can destroy this one, and I can create a new one, which then could, for instance, be that one. This operator is normally called a one particle, one hole excitation operator. So we will often label this one a one particle, one hole term. This is not the full Hamiltonian, because if we were to take the full interaction piece, we would normally have something which would go like this, and then some matrix elements, which I just leave unspecified. And then I would have an A alpha, A beta, A delta, A gamma. And these runs over all the possible slots which I have. So what we have done now is to make a limited Hamiltonian, where we just picked some specific terms, which often are some of the correlations you find in many-body physics or in quantum physics, which are sometimes the most important ones. Because often what you have is a two-body operator, and that acts typically at two particles at a time. So what you will often see in many other type of calculations is that correlations between two particles are some of those which give a dominant contributions to the total energy. In addition to the one-body term, which can often be defined by an external potential. Like if you look at the atomic systems, you have a attractive potential from the atomic nucleus, which confines the motions of the electrons. And that is a very important contribution to the total energy of the system. And then the two electrons can interact and repel each other. And that is also another important contribution to the energy. Okay, so this is the basic idea behind this model, is a simplification of the full Hamiltonian in terms of some terms which we think are relevant to describe the physics of the system. Now, in the first exercise, you actually ask to rewrite the Hamiltonian. In the first set of exercises, you actually ask to rewrite the Hamiltonian in terms of the operators for spin. So let me just quickly remind you of the commutation relations for angular momentum, because that's something you will need in solving the exercises. So commutation relations for angular momentum. So if you now assume that A is a vector, so you can define a component like A plus, which is typically given. So you can sometimes have a sum over 1 over square root of 2 of A x plus I times A y. I guess you've seen these kind of notations before. And then you have a similar one with A minus. So these are just the x and y components, ax minus a times I times ay. And then we have a az term, which is just the c components of a vector. So it's pretty common because for angular momentum, one of the things, I don't know how much you remember from that, but you will often find that one of the components is independent of the two other ones, whereas the x and y component can depend on each other. So it's pretty common then to make a linear combination of the x and y components. And the commutation relations, which you may have seen between, let's say, an operator for angular momentum, Jz, is equal to minus plus, a plus minus. I'm putting h bar equal to 1. I have a plus with j plus minus. So these are two different vectors. This is equal to 0. I have a plus minus with j minus plus, which is equal to plus minus. And then it has 2 times az. And then we have additional relations here where we have a z plus minus, which is equal to plus minus a plus minus. And finally, I have the relation between A, Z with JZ, which is equal to 0. And yeah, that A could be J. Just any operator. And these are vectors, right? Like J is a vector with X, Y, and Z components. And A is a vector with X, Y, and Z components. And these are the commutation relations which you may find in standard textbooks. So what we are going to do now is to define operators. And you can see now if we define a J plus in a second quantized way as a sum over the states P, and I have an A plus and an AP minus. So what this is doing is just creating, you have annulating a particle with minus spin, and it's promoting it up to a plus spin. And J minus is equal to P of A of P minus, and then A of P plus. So these are the spin values. So sigma is equal to +1 or -1. And then I define this JC here as a sum. I'm putting this as a half. And then I'm summing over all the spin values of sigma times AP sigma of AP sigma. So let's see now if these definitions obey the commutation rules for angular momentum. So this is just what you see here is a suggestion. Now let's see if this can satisfy this rule. So when people did this in the beginning, they played around with different combinations. So what we would like to now, if we go back to the commutation rules, is to see whether J plus and J minus, whether that is equal to 2 times JC. So if you go back, we have now this relation here, which says that if I now look at a term like this one, I should get now this term here, this one actually. And now the spin is equal to a half. Okay, so let's see if we can get that. And let's plug in these expressions which we had for the operators. So that is going to be equal to a sum over P and P prime. And now I'm simply setting up the commutator. So this is going to be given by AP plus, AP minus, and then I have AP prime minus and AP prime plus, like that. So that I'm just setting up the commutator between these two quantities. And since these represent multiplications between the operators, I have to have a double sum of P and P prime. So the exercise is not the most exciting one. It's actually, exercise A is a little bit boring in a sense, because you're gonna get lost sometimes in all these indices. But let's just write it out here. So if we write it out, what we get then is just a sum over P and P prime. And now I'm just collecting these terms here. So I will have an AP plus, AP minus, and then AP prime, AP prime, and then it's plus, minus, and then I have AP prime minus, AP, now I have to be careful, so I have all the, and this is multiplied with AP plus, AP minus, like that. Now, remember now that when we are calculating such a commutator, this is something which is acting on a state. And the standard approach, which we typically do then, is to use the anti-commutation rules for the operators. So if I now use the anti-commutation rules on these two guys, so I actually normal order it, that will give me a Kronecker delta, where delta P will be delta P and P prime. So that is going to take away one of the sums over P of P prime. So we were going to get a term. So the first term gives us P, and then I have an AP plus, AP minus. And then the second term, when I now interchange the operators and get the Kronecker delta, I'm going to get an AP minus of an AP minus, like that. And then there's going to be a new term, which goes like P prime. And this is going to have a minus, an AP plus. You can quickly get lost in all the indices. Even if I've done this many times, it's easy to interchange some of them. Plus, and this has a plus as well. That's the second term which I have. When one term here gives me the Kronecker delta, which leads to this term. And then when I perform the Kronecker delta and have the anti-commutation, then I get this term, and then I have a second term, which now should read, sorry, plus, and then I have a P prime minus AP plus AP prime plus AP minus. Now, if I look at what I have now, wait a moment, that should be, yeah, that should be P minus, yeah. I can simplify this one, one of these terms here, and then I can actually get this one equal, when I sum this up, to a sum over P, and then I have AP dagger plus AP plus, and okay, so that's that one. Plus and minus an AP minus, an AP minus here. And that is nothing but the term P sigma of the sigma of AP sigma dagger of AP sigma, which is the same as 2 times JZ. Okay, so you can do something corresponding to that one. So this is not the most exciting exercise to do. You will also find that if you take J minus with J plus, that is going to be equal to minus J plus J minus. And that's going to be equal to minus 2 times JZ. One which is trivial to show is actually that JC of JC has to be equal to 0. And then finally, one of the other relations which are going to show, which is the most tedious case, is actually the one where you take one of these operators plus minus, and you have to show that one to be equal to 0. So that's another not too exciting exercise. Yeah. No. It's just one of the exercises, because in the midterm, we are going to look at the Hamiltonian, because at the end, you can actually rewrite the Hamiltonian, which we had, in terms of these angular momentum operators. So when you collect everything, you're going to see that you can write the Hamiltonian in terms of the following terms. So let me just write this one. So, and this is the I think this is exercise B. So you can actually write H0 in terms of this epsilon times JC. Then you will see that H1 is going to be equal to 1/2 times V times J plus squared plus J minus squared. epsilon is just the single particle energies which you have. So it is epsilon which you have here, which we put up in the very beginning. So this epsilon is then going to refer to the single particle energies you have here and here. And it's actually normally just given in terms of a constant gap here, just a constant. Because the spin value, if you look here, if you put that to a constant, then if you have spin plus, then it's just +1 or plus epsilon, and the other one is minus epsilon. So this is just a constant which represents the single particle energies. So you can then rewrite this one in terms of Jz, and you will also be able to rewrite this one in terms of this constant, and then it contains J plus, J minus, plus J plus, J minus, minus the number operator. So I've forgotten to put hats on all these guys, because these are now operators. Okay. Now the thing, why is this interesting? It's interesting because you can use the ladder operators for creating states. You will start with a state which has the total spin equal to -2, which would correspond to you being in the lowest state. Then you can actually, with these operators, J plus, J minus, you can act on a state of MS and create the next state. And you have this, and this gives actually rise to a coefficient, which is normally called a Clebsch-Gordon coefficient of MS. So this is given by MS plus -1. And that coefficient is given by your value of S times S plus 1 minus the MS value times MS plus -1 multiplied with MS plus 1, that specific state. Now, your Hamiltonian is so that if I have different MS values, it preserves. So you will also see that the Hamiltonian commutes with these quasi-spin operators. So that means that your Hamiltonian is going to obey a property which is actually going to be proportional with MS and MS prime. So I'm putting proportional because there are constants in addition. So that means that you can actually set up a Hamiltonian matrix elements with this basis state. Yeah. Thanks. So I will say a little bit more about this tomorrow as well during the lecture. But I wanted to prepare you for the boring part. And this is just an exercise in using the commutation and anti-commutation relations. Commutation relations for angular momentum and anti-commutation relations for the creation and annihilation operators. So if you define these operators here, you can actually show that they behave like a spin type or angular momentum type of operators, and that they have the same commutation relations. And then we can rewrite the Hamiltonian in terms of these operators. And when these guys act on one of these states, like if this operator here acts on, let's say, a state with a given number MS, this is going to be given by a constant times this MS. So that's going to simplify the setup of the Hamiltonian matrix. So there's a lot of intermediate calculations, but the nice thing with this Lipkin model is that it actually allows you to set up a Hamiltonian matrix problem, which is much simpler than if you were to go through the operation of these Hamiltonians on all the possible realizations of states. So if you have a lot of spare time, you could actually try to calculate the action of that Hamiltonian on all these 70 states. I will never give such an exercise. You would hate me forever. Yeah.
Last slide.
The last. Just say stop. This one. Oh, oh. This is actually me. Sorry. Plus J minus J plus. Sorry. Yeah, even if you have it in front of you, and then you write it on the whiteboard or blackboard, there's a translation problem. Thanks.